Welcome to the Deep Dive.
Hey there.
Today, we're taking off into the fascinating world of digital technology in modern aircraft.
That's right.
Our listener, the learner, sent over a really fantastic set of materials.
Yeah, it's quite the collection.
We're going to unpack everything from, those sleek electronic displays in the cockpit to the fundamental computer concepts powering them.
And the digital communication networks, the software, even things like electromagnetic interference. It's all in there.
It really is comprehensive. Okay, so let's lay out our mission for this deep dive.
Right.
We want to extract the essential knowledge, right? How these digital systems function in planes, why they're absolutely crucial today, and what goes into their design and maintenance.
Exactly. We want to make it clear and engaging for you, our listener.
Yeah, we'll be your guides. Try to cut through the jargon and highlight what's really important to understand.
Precisely. It's about getting a solid grasp of the core ideas, how they all fit together to make modern flight possible without getting bogged down in, super heavy technical stuff.
Okay, let's start where the pilots sit the cockpit. This shift to digital, it wasn't like flipping a switch, was it? We started with analog.
Not at all, no. If you picture older aircraft cockpits, you see banks of round analog dials, often in that classic T arrangement.
Right.
And while those mechanical instruments work the move to electronic instrument systems, or EIS, the glass cockpits, brought huge advantages.
More reliable, fewer moving parts.
That's a big one, yeah. Less prone to mechanical failure. But even more importantly, EIS allowed integration.
Combining functions onto one screen.
Exactly. Multiple flight navigation functions on a single display. This really gives the crew a much more unified picture. Better situational awareness.
So less time scanning, more time understanding the big picture. When did these glass cockpits really start showing up in commercial jets?
Well, the first commercial airliner with EIS was actually the McDonnell Douglas MD-80, way back in 1979.
Wow, that early.
Yeah, but it used CRT technology, like old tube TVs. Heavy, hot.
Ah, okay.
The real game changer came later with LCDs, liquid crystal displays.
Right. Lighter, less power hungry, less heat. That must have been a massive improvement for aircraft design.
Absolutely massive. Weight, space, power consumption, heat, all critical factors. And these glass cockpits, they vary quite a bit. A small plane might have 1 or 2 screens. A big airliner could have 5 or more.
So what does a more advanced setup look like? Take, say, a Boeing 777. How do its displays work together?
Okay, the 777 is a good example. It typically has independent displays for each pilot, but the key is that each display is driven by its own display processor unit, often called a symbol generator.
Like a graphics card for the plane?
Kinda, yeah. It takes data from all over the aircraft, flight director, navigation systems, air data, weather radar, crew inputs, and paints the picture on the screen.
Okay, processing all that incoming data. So what are the main displays pilots are looking at?
There are a few key ones. The primary flight display, the PFD, is absolutely central. It replaces the old attitude indicator and shows everything critical for controlling the plane right now.
Like attitude, airspeed, altitude.
Yeah, exactly. Attitude, airspeed, altitude, vertical speed, heading, plus alerts, maybe TCS info. It integrates it all into one composite display. Much easier to read quickly.
Makes sense. All the core flying info in one spot. What about navigation? Where does that show up?
That's primarily on the navigation display, or ND. It shows your heading, your route, signals from VORs, GPS, ILS guidance, usually overlaid on a moving map.
And you can layer more info on that.
You can.
Yeah.
That's the beauty of it. Weather radar data, waypoints from the flight management system, terrain info sometimes.
Yeah.
It really builds a comprehensive picture of where you are and where you're going.
Super useful. Now, I've also heard the term EICAS. What's that about?
ECAS engine indication and crew alerting system. Does what it says on the tin, really.
Okay.
Displays key engine parameters, pressure, speeds, temperatures, thrust modes. But critically, it also provides alerts. System failures, warnings, cautions.
In a graphical way.
Yes, often graphically. If an engine oil pressure drops, for example, EITs might give an audible warning and highlight the affected engine parameter, maybe show it in red on a display. It draws your attention right where it needs to be.
So it's proactive, not just passive display. It seems like a big safety boost.
Definitely. And often working alongside EICAS is the multifunction display, or MFD.
Multifunction. So it does lots of different things.
Pretty much. It's flexible. Can be a secondary engine display, show system status pages like fuel, hydraulics, electrics, comms, info, maintenance data, even electronic checklists or diagrams of the aircraft systems.
Wow, okay. It sounds like these digital cockpits really transformed how pilots interact with the plane. Much more integrated, much safer.
Fundamentally changed it, yeah.
All right, so these systems are processing tons of digital info, which brings us to the basic language they speak. Numbering systems. Why is binary the default?
It boils down to the electronics themselves. At the most basic level, digital circuits understand two states, on-N or OFF, voltage or no voltage.
Like a light switch.
Exactly. And binary base 2 uses just two digits, 1 and 0. It's a perfect match. 1 for on, 0 for off. It's the native tongue of digital hardware.
Okay, natural fit. But we think in decimal, base 10. How does the conversion work? Decimal to binary.
It's a process of finding powers of 2. I take your decimal number, say 100. What's the biggest power of 2 that fits into it? That's 64, which is 2 to the power of 6.
Okay.
So you put a 1 in the 64's place. Subtract 64 from 100 leaves 36. Biggest power of 2 and 36 is 32, or 2 to the 5.
So 1 in the 32's place.
Right. Subtract 32 leaves 4,
Yeah.
which is exactly 2 squared. So 1 in the 4's place. You fill in the rest with zeros. So 100 in decimal becomes 100, 100, 100 in binary.
Got it. Step-by-step subtraction using powers of 2. And going the other way, binary back to decimal.
Even simpler, really. You just add up the decimal values for every position where there's a 1. For a 100, 100, you add 64 plus 32 plus 4 equals 100.
Straightforward. Now, the sources also mention octal and hexadecimal. Why bother with those if the computer just uses binary?
They're basically shorthand, especially for humans reading or writing code. Long strings of binary ones and zeros get really cumbersome, easy to make mistakes.
Right.
Octal is base 8, hexadecimal is base 16. Because 8 and 16 are powers of 2, converting between them in binary is easy. You just group the binary bits.
How does that grouping work?
For octal, you group binary digits in 3s. For hexadecimal or hex, you group them in 4s. Each group then corresponds to a single octal or hex digit.
Ah, so it compresses the information visually. Hex uses letters too, right? A through F.
It does. Since base 16 needs 16 symbols, it uses 0 through 9, and then A for 10, B for 11, up to F for 15. Each hex digit represents exactly 4 binary bits.
Can we convert our decimal 100 to hex?
Sure, we know 100 is 011 0 100 in binary, adding a leading 0 to make 8 bits, 2 groups of 4.
Okay.
Group them, 019 and 0100. Convert each group. 0100 in binary is 6 in decimal and hex. 0100 is 4 in decimal and hex. So 100 decimal is 64 hex. Much shorter than 011010
Definitely cleaner. And octal. Same idea with groups of 3.
Same idea. Binary 01100110. Group in 3s from the right. 001 100 100. Adding leading zeros. 001 is 1, 100 is 4. 100 is 4. So 100 decimal is 144 octal.
Got it. So different ways to represent the same underlying binary data, mostly for human convenience. One last term here, least significant bit, LSB.
The LSB is just the bit on the far right in a binary number, the one in the 2 to the 0 or 1's place. It has the smallest value. Its change has the least impact on the total number.
Yeah.
Like the one's digit in decimal.
Okay, clear. So we have the digital language. How does this data actually get around the aircraft? That's where data buses come in.
Exactly. Early aircraft had point-to-point wiring, miles and miles of it. Heavy, complex, lots of potential failure points at connections.
A nightmare to troubleshoot, I bet.
Oh, absolutely. So the industry moved to data buses. Think of them as shared highways for digital information. Multiple systems can send and receive data over a common pathway, drastically reducing wiring.
Much more efficient. What are some common beta bus standards we see in planes?
Well, a really important one, especially in military aircraft, but also some commercial, is MEL STD 1Feed 5E3B, often just called 5E53B.
Okay. What are its key features?
It's an asynchronous half-duplex bus. Half-duplex means data flows both ways, but only one direction at a time, like a walkie-talkie.
Right.
It has a central bus controller, the BC, that manages everything. It tells specific remote terminals, or RTs, the devices connected to the bus, when to send or receive data. RTs can't talk unless the BC tells them to.
So the BC is the traffic cop.
Pretty much. It sends command words. The RTs respond with data words or status words. There's often a bus monitor, too, just listening in to check for errors. The whole thing runs over shielded twisted pair of wires and, crucially, uses isolation transformers at each connection.
Why the transformer?
For fault isolation. If one RT shorts out, the transformer prevents it from taking down the entire bus. Very robust.
Makes sense for critical military systems. What about the commercial side? They use 1553 too.
Sometimes, but a very common standard, especially in slightly older airliners like the 757, 767, A300, A310, is AIR-INC 429.
AIR-INC 429, different from 1553.
Quite different. It's simpler, cheaper, but less robust. Big difference. It's simplex. Data only flows one way on a given wire pair, like a one-way street.
So if a system needs two-way comms.
It needs two separate AIR-INC 429 buses, one going each way. It also has a lower data rate than 1553 and limits on how many receivers can listen on one bus, usually up to 20.
Simpler, but with limitations. What about newer planes like the 777 we mentioned? What does it use?
The 777 introduced ANC 629. That was a big step up. Much faster 2 megabits per second compared to 100 kilobits for ANC 429 typically.
Oh yeah, quite a jump.
Yeah, and it can handle more terminals, up to 131. Plus, it's multiple source, multiple sync, and doesn't need a central controller like 1553.
How does it manage traffic then? Avoid collisions?
It uses a clever time-based protocol. Each terminal knows its specific time slot when it's allowed to transmit. Keeps everything orderly without a central boss. It also uses a special serial interface module for isolation.
Interesting, like everyone gets their scheduled turn to speak. Now, the sources also mention Ethernet and aircraft networks. How does standard computer networking fit in?
Ethernet, the same IE 802.3 you find in offices, has been adapted for aircraft. Initially more for non-critical things like in-flight entertainment, but its use is growing.
Using twisted pair or fiber optics?
Both. Twisted pair for lower speeds, fiber for higher speeds, and better EMI resistance. Uses hubs or switches. Source and destination addresses in data frames, error checking very similar concepts to ground-based Ethernet, just adapted for the airborne environment.
Leveraging existing tech? What about FireWire, IEE 1394? I know that from old computers and cameras.
Yep, FireWire also found a niche, again, often in high-bandwidth applications like IFE video streaming. But interestingly, it's also used in some very critical systems like the flight and engine controls on the F-35 fighter.
Really? Why the...
High bandwidth, and it has good fault-tolerant characteristics built in. There's also AFDX, avionics full duplex, switched Ethernet, which is becoming very common in newer designs like the A380 and A350. It's basically a specialized version of switched Ethernet designed for deterministic, reliable avionics communication.
Fascinating how these different standards coexist, chosen for specific needs. Okay, so we have the language, the communication lines. What about the actual thinking, the logic circuit?
Right, logic gates. These are the absolute fundamental building blocks of all digital circuits. They're made up of transistors acting like tiny electronic switches.
And they manipulate the ones and...
Exactly.
Yeah.
They take binary inputs and produce a binary output based on a specific logical rule. Millions of these can be packed onto a single integrated circuit chip.
What are the basic types of gates?
The real basics are NOT, AND, and OR. A NOT gate or inverter just flips the input. 1 becomes 0, 0 becomes 1.
Simple enough.
An AND gate needs all of its inputs to be 1 for its output to be 1. If any input is 0, the output is 0. Think this AND, that must be true.
Oh.
An OR gate outputs a 1 if any of its inputs are 1. It only outputs 0 if all inputs are 0. Think this OR, that must be true. There's also a buffer gate, which just passes the input through unchanged, mainly used for signal driving.
And they have unique symbols and diagrams, right? And truth tables.
They do. Standard symbols help read circuit diagrams. And truth tables are essential. They list every possible input combination and the resulting output for a gate. Makes the logic very clear.
Okay, those are the basics, but there are more complex ones.
Yep, built from the basics. NAND is not, and its output is the opposite of an AND gate, nor is NOT OR, opposite of an OR gate.
Inverted outputs. What about XR and XNOR?
XOR stands for exclusive OR. It outputs a 1 only if the inputs are different. So 0 and 1 gives 1, but 0 in a row or 1 and 1 gives 0.
Ah, exclusive. Only one can be true.
Kind of, yeah. Or more accurately, they must be different. XNOR is exclusive, nor the opposite. It outputs a 1 only if the inputs are the same.
Okay, useful for comparisons. I also saw negative logic gates.
That's mostly about convention. In negative logic, a low voltage might represent a 1 and a high voltage a 0, the opposite of positive logic. The underlying gate function, AND or R, is the same, but the interpretation of voltage levels is flipped. Symbols often have little circles on the inputs or outputs to show this inversion.
A bit confusing, but offers design flexibility, I guess. Do these simple gates actually get used in, say, a warning system?
Absolutely. The source had a simple example. A door warning. Maybe you want a cockpit light if the cabin door or the baggage door is open.
Okay.
Each door has a sensor, 1 if open, 0 if closed. Feed those into an OR gate. If either sensor is 1, the OR gate output is 1, turning on the warning light.
Makes perfect sense. A simple OR condition. So combine enough of these gates and you get a complex processing, which leads us to basic computer structure.
Right. At the heart of it, any computer has 3 core parts. The CPU, the central processing unit, that's the brain, executes instructions. Memory stores the instructions and the data the CPU works on. And the I/O system, input-output, how the computer talks to the outside world. Sensors, displays, actuators.
CPU, memory, I/O. Got it. And some basic terminology. Bit, byte.
Sure. Bit is a single binary digit, 0 or 1. Byte is usually 8 bits. Software is the instructions, the programs. Hardware is the physical stuff. IC is an integrated circuit, the chip itself.
How does the CPU actually run the software?
It follows a cycle. Fetch an instruction from memory, decode what the instruction means, then execute it. This cycle repeats over and over, driven by the computer's clock.
The clock speed, measured in gigahertz.
Exactly. Billions of cycles per second. Each cycle lets the CPU perform a tiny step. Faster clock generally means faster processing.
And memory types. You mentioned RAM, ROM.
Right. RAM is random access memory. It's read-write, where the computer holds currently active data in programs. But its vol loses data when power's off.
Okay. Temporary workspace.
ROM is read-only memory. Non-volatile holds permanent data like startup instructions. Can't be easily changed. PROM is programmable ROM. You can write to it once, then it's read-only.
Got it. RAM for active work, ROM for permanent stuff. And how are these chips physically mounted? DIPs?
DIP, dual inline package, is a common way to package ICs. It's that rectangular black chip with 2 parallel rows of pins. Standardized way to plug chips onto circuit boards. Makes assembly and replacement easier.
Standardized components. Now, aircraft computers versus, say, my laptop, what are the big differences? They must be built differently.
Hugely different design constraints. Aircraft computers need to survive extreme temperatures, vibration, acceleration, shock, things your laptop thankfully doesn't face.
Definitely not.
They also need to be incredibly reliable, often fail-safe certified. A software crash in flight is, well, unacceptable. The level of testing is orders of magnitude higher.
Makes sense. Lives depend on it. How about interfaces?
They interface with specific aircraft systems via those data buses we talked about, ANC, 1553, etc. And they have specialized peripherals. An FMC flight management computer talks to cockpit displays, a data loader, the CDU keyboard.
CDU is the control and display unit.
Right, that little keyboard and screen pilots use to interact with the FMS. And redundancy is key. Critical systems always have backups.
Robustness, reliability, redundancy. Got it. Briefly, serial versus parallel buses and compilers versus interpreters. How do they apply here?
Serial buses send data 1 bit at a time. Parallel send multiple bits at once. Parallel is faster for short, internal connections like inside a computer case. Serial uses fewer wires, better for longer external connections like those aircraft data buses.
Okay. And compiler versus interpreter.
Both translate human-written code into machine code. A compiler translates the whole program at once, creating an executable file. An interpreter translates and runs it line by line.
Which is used in avionics.
Compiled code. It runs faster and more predictably, which is essential for real-time, safety-critical systems. Interpreted code is generally too slow and less deterministic for flight controls or navigation.
Right. Need that speed and reliability.
Yeah.
Okay, switching gears a bit. Protecting these sensitive electronics. Electrostatic discharge, ESD. What is it and why the fuss?
ESD is that sudden zap of static electricity, like shuffling on carpet then touching metal. Even tiny discharges you don't feel can fry sensitive electronic components.
Fry them, like permanent damage.
Absolutely. Can cause immediate failure or worse, latent damage that only shows up later, maybe during flight. The heat from the discharge can melt tiny internal structures or break down insulating layers.
That's scary. Which parts are most vulnerable?
CMOS chips, very common in digital logic, are extremely sensitive. Hundreds of volts can damage them. Bipolar transistors are a bit tougher, but still vulnerable. EEPROMs used in memory can be damaged by just 100 volts, and you could easily build up thousands of volts just walking around.
Yikes. Okay, so how do technicians protect against this invisible threat?
It's all about creating ESD-protected areas, or EPAs.
No.
Workspaces designed to prevent static buildup and discharge. Grounding is key.
Grounding.
Connecting everything conductive, the work surface, the tools, the technician, to a common electrical ground point, so any static charge flows away harmlessly. This involves special conductive floor mats, table mats, usually with resistors built in for safety.
And the technicians themselves. Wrist straps.
Exactly. Anti-static wrist straps connected by a cord, again with a safety resistor, to the common ground. Must be worn snugly against the skin. There are also grounding test stations to verify the straps are working before you start handling components.
A whole system to drain static safely. What about materials that don't conduct electricity, like plastics, ionizers?
Right. Insulators can hold a charge, but it can't be grounded easily. Ionizers flood the air with positive and negative ions, which neutralize static charges on nearby insulating surfaces. Very important for controlling the whole environment.
Clever. And handling the components themselves.
Always handle them in an EPA, wearing your wrist strap. Transport and store them in special static shielding bags or containers. Keep them in those bags until the moment you install them. Use grounded tools, like soldering irons. Discharge yourself before touching anything sensitive. Keep regular plastics and insulating materials away from the bench. Even clothing matters. Cotton is better than synthetics. Sometimes special smocks are required.
Sounds incredibly meticulous. Okay, beyond static, what about the broader electromagnetic environment? EMI.
EMI, electromagnetic interference. Basically, electrical noise that can disrupt electronic systems. Can come from inside the aircraft or outside.
How does this interference couple or travel?
4 main ways. Radiative, noise travels through the air like radio waves. Inductive, changing magnetic fields induce currents in nearby wires. Capacitive, changing electric fields induce voltages. Conductive noise travels along shared wires, like power or ground lines.
So it can jump through the air or travel along wires. What about HIRF, high-intensity radiated fields?
HIRF refers to very strong electromagnetic fields, powerful enough to potentially disrupt or damage electronics or even harm people. Think high-power radar broadcast towers. Aircraft themselves have powerful transmitters, so managing interference between onboard systems is also crucial.
So the plane can interfere with itself?
Potentially, yes, if not designed carefully. And then there's lightning.
A massive natural source of electromagnetic energy.
Huge. A lightning strike creates a massive electromagnetic pulse, EMP, that can induce damaging currents and voltages in aircraft wiring and electronics.
How do planes survive lightning strikes, which happen fairly often?
Through careful design. Lightning detection systems help avoid the worst storms. Protection involves providing a conductive path for the current to flow safely through the aircraft structure, the skin, bonding straps, and exit via static discharge wicks. Grounding and shielding of wiring is critical. Composite aircraft need special conductive layers or mesh built in.
Maintaining that protection during repairs must be vital.
Absolutely. Any damage to conductive paths needs proper repair to maintain lightning protection. Which brings us to EMC, electromagnetic compatibility.
The overall goal.
EMC is about ensuring all electronic systems can operate correctly together in their intended electromagnetic environment. It involves 2 sides: reducing emissions from devices, using shielding, filtering, and increasing the immunity of devices to interference. Wiring separation, grounding, bonding, shielding.
Making sure everything plays nicely together, electromagnetically speaking. What's the technician's role in maintaining EMC?
It's critical. Proper installation, ensuring grounding and bonding are intact, correctly reassembling shielded enclosures, LRUs often act as Faraday cages, ensuring cable shields are terminated correctly. Any lapse can compromise EMC and potentially affect system reliability.
So maintenance procedures are key. Okay, we've covered hardware, environment, let's talk software. Millions of lines of code in modern planes. Why is controlling that software so vital?
Because a software error in a critical system flight controls, navigation can be catastrophic. Unlike hardware failures that might degrade gracefully, a software bug can cause sudden, unexpected, and dangerous behavior. So rigorous control over development, testing, and updates is paramount.
Makes sense. What standards govern this? I saw DO 178B mentioned.
DO 178B and its European equivalent ED 12B were the cornerstone standards for years. They define processes and objectives for developing safe airborne software. The FAA, EASA, and other authorities use it for certification.
And it has different levels based on risk.
Yes, design assurance levels, DALs, from level A, catastrophic failure condition, down to level E, no safety effect. A flight control system is typically level A. Cabin entertainment might be level E. The higher the level, the more rigorous the development and verification process is required.
More critical system, tougher rules. Can you mix different levels on the same computer?
Yes, using specific partitioning techniques like those defined in ARIN 653. This allows different applications to run on the same hardware, but keeps them isolated in protected memory and time partitions. So a bug in a level E system can't crash a level A system running alongside it. Crucial for integrated modular avionics, IMA.
Protecting the critical stuff. Now, DO 178B has been updated to DO 178C.
It has. DO 178C came out in 2011 to address newer software development techniques, especially model-based development and verification, and the use of software tools.
Model-based.
Using graphical models to design and even automatically generate code, using tools like MATLAB Simulink. DO 178C provides guidance on how to verify software developed this way. It also has supplements covering tool qualification, object-oriented programming, and formal methods using mathematical proofs for verification.
Sounds like it keeps pace with evolving technology. Does it emphasize traceability?
Very much so, especially at level A. You need clear links between requirements, design, code, tests, and even the final executable object code loaded onto the aircraft. Level A also requires demonstrating software robustness, how it handles errors and unexpected conditions.
Extremely thorough. Okay, let's put it all together. How do these individual systems form a coherent whole in a modern aircraft? IMA.
IME, Integrated Modular Avionics, is the architectural philosophy. Instead of lots of separate black boxes each doing one thing, IMA uses common computing modules that can run different software applications, shares resources, saves weight, power, cost.
So hardware modules might be identical but run different software for different jobs.
Exactly. And IMA relies heavily on those robust data buses and partition schemes we discussed. It also usually includes comprehensive built-in test equipment, byte-E, for fault detection and maintenance.
What core functions are typically part of an IMA system?
Communications, navigation, ADF, VOR, ILS, GPS, etc., surveillance, transponders, TCS, and information systems. The cockpit displays EICAS, EFIS, ECAS, all talking to each other over the network.
Like the equipment racks on the 777 you mentioned earlier.
Precisely. Racks full of modules, AIMS cabinets, airplane information management system, ADRUs, air data inertial reference units, flight control computers, autopilot directors, all interconnected.
Speaking of ADRUs, how do inertial reference systems work now, still spinning gyros?
Less often mechanical ones. Ring laser gyros, RLGs, became common. They use laser beams traveling in opposite directions around a cavity. Tiny changes in path length due to rotation are measured very accurately using the Sagnac effect.
Lasers instead of spinning masses.
Right. And even newer systems use MEMS, microelectromechanical systems. Tiny vibrating silicon structures that sense motion, even smaller, lighter, more reliable.
Amazing miniaturization. What about the flight management system, the FMS? That seems like a major digital hub.
It really is. The FMS automates a huge part of navigation and performance management. Pilots input the flight plan, performance data. The FMS takes that, plus real-time data from GPS, IRS, navigation radios, air data.
And calculates the optimal path.
Calculates the best lateral and vertical path, considering winds, fuel burn, restrictions. Then it provides guidance to the autopilot and flight director, and displays everything on the ND and the CDU, usually dual redundant FMCs for safety.
The brain of the flight plan. And TCAS, the collision avoidance system, how does that fit in digitally?
TCAS is an independent system. It actively sends out interrogation signals on one frequency, 230 megahertz, and listens for replies from other aircraft transponders on another, 1090 megahertz.
Like asking anyone nearby.
Essentially, yes. Based on the replies, it calculates the range, bearing, and relative altitude of other traffic. If a potential collision threat is detected, it issues alerts. First, a traffic advisory, TA, look out. Then, if necessary, a resolution advisory, climb or descend, coordinated with the other aircraft's TCS if it has one. Displays the traffic on the PFDND.
A crucial digital safety net. Now, flight controls themselves. We went from cables and pulleys to fly-by-wire.
Big shift. Fly-by-wire replaces the direct mechanical links. Pilot moves the control stick or yoke that sends an electrical signal to flight control computers.
Not directly moving surfaces.
No. The computers interpret the pilot's command, factor in airspeed, attitude, configuration, stability requirements, and then send commands to actuators, hydraulic or sometimes electric, that move the control surfaces, ailerons, elevators, rudder.
So the computer is mediating the control.
Exactly. Allows for stability augmentation, flight envelope protection, more optimized control. Systems like on the Boeing 777 or Airbus planes rely on this. It also enables things like sophisticated autopilots and auto land.
Incredible. Finally, even the cabin has gone digital, right? Beyond just movies.
Oh, yeah. In-flight entertainment, IFE, is now highly interactive. Internet access via Wi-Fi, cell phone connectivity, sometimes streaming video, ordering food. It requires a sophisticated cabin network, often using Ethernet or Firewire, managed by a communication server.
And linking to the ground.
Often via satellite communication, SATCOM. This digital backbone also supports things like HEMS health and usage monitoring systems.
Monitoring the plane's health.
Yes. Collecting data from sensors and byte systems across the aircraft, analyzing trends, spotting potential problems early, can even transmit data to ground maintenance crews proactively.
So digital tech permeates absolutely everything. Wow. This has been incredibly thorough, a real deep dive. To wrap it up, what are the absolute key takeaways?
I think the main thing is that digital tech is fundamental to modern aviation now. It enables huge capabilities, better control, navigation, information, efficiency, safety.
But it comes with demands.
Absolutely. It demands extremely careful design, totally reliable communication networks like those data buses, logical processing, very robust protection against things like static and interference, and above all, incredibly rigorous software control under standards like DO-178C. It's complex, but essential.
Well put. It really makes you think. With this ever-increasing complexity and interconnectedness, what do you see as the next big challenge or innovation for safety and efficiency in air travel? Where does it go from here?
That is the big question, isn't it? Cybersecurity is definitely a growing concern protecting these complex networked systems. And maybe further integration of AI, perhaps in flight management or decision support, which raises fascinating questions about certification, trust, and the human-machine interface in the future.
Definitely things to keep an eye on. Well, if you, our listener, found this fascinating, maybe dig deeper into DO-178C or explore specific data buses like AFDX or ARIN NC629. There's clearly a whole complex world operating beneath the cockpit floor.
Absolutely. It's a constantly evolving field.
Thanks for joining us on The Deep Dive.